Yeah, so this is a no-code overview of a ubiquitous but underappreciated feature of basically all game engines, which is the animated sprite. It's a high-level and fun and breezy overview of some gnarly topics like linear algebra, OpenGL, and shaders. But mostly it's to help users of engines like Unity or Godot or Unreal appreciate the work that goes into some of the out-of-the-box features of those engines. Everything you need to know about me is on this slide. And here's the final result. Look at this cute animation. The sprite work was done by my friend Jade, who's in the audience. Say hi, Jade. So let me ask you, how hard could it be? In an engine, you should be able to make this in, what, a couple minutes? Without one, well, okay, so what is a flipbook? A flipbook simulates motion by showing images in rapid succession such that persistence of vision gives the illusion of motion. And this up here is a sprite sheet, and every one of those images is a frame of animation. All those images are stored together in a single picture. We only show part of the image at once, and that's how we get our flipbook effect. Graphics APIs. If we're writing our own engine, which you shouldn't, I have a whole talk about that, we need to pick one or more graphics APIs to support. We use these APIs to talk to the graphics card. So OpenGL, it's cross-platform, it's relatively easy to use. Again, relatively is in big air quotes here. There's Vulkan, which is cross-platform. It's really hard, and it needs reasonably modern hardware to run it. There's DirectX, which is Microsoft, it's proprietary, it's Windows and Xbox only. There's Metal, which is Apple, and it's proprietary. It's for iOS and macOS. And they deprecated OpenGL relatively recently, so it's really hard to get OpenGL apps to run on Mac anymore. There are proprietary PlayStation and Switch APIs, but the Switch does support OpenGL and Vulkan, so that's nice. OpenGL is the obvious choice for us. Isn't this exciting? Before we can do anything else, we need to create a window. How hard could it be? So we're going to initialize this library called glfw. That's a library that handles opening windows and reading user input. We need to actually create a window. We need to use loadglad. That's a library that loads all of that juicy OpenGL functionality. It's needed on Windows because Microsoft deprecated support for OpenGL in the 90s. We need to set a clear color to this sort of lovely forest green. We need to set the swap interval. Basically, do we want vsync or not? We set a viewport that tells OpenGL how much space it has to draw on. And then, over and over in a loop, we process input. We handle inputs like the user closing the window or something like that. We clear the screen with our clear color. We swap the buffers. We have two drawing surfaces. One of them is the one that we're actively showing, and the other one is the one that we draw to, and then we swap them. And of course, when we close the window, we have to call glfw terminate to clean up our mess, basically. And we get a blank screen. Sheesh. When a graphics programmer shows you something unimpressive, just say nice things about it. It was probably really hard. Shaders. You've probably heard of shaders, but what are they really? There are two, the TLDR is that they're little programs that run on the graphics card. There are two kinds that we care about, vertex and fragment shaders. Vertex shaders run once per vertex, and we can move them around. Fragment shaders run once per pixel, sort of. Fragments aren't pixels, but I have 20 minutes, don't worry about it, it's fine. They're pixels. There are several other kinds, but this talk is long enough. Our simplest vertex shader does essentially nothing, it's just pass through. Our simplest frag shader returns a solid color. And we can compile and link those suckers into a single shader program. Here's the data for two triangles, making up a quad. Each vertex has an x, y, and z coordinate. I said no code at the beginning. I lied. Here's a little c. Now, we have the data for the quad. How do we draw it? Well, we need to create something called a vertex array object. Don't worry about it. We need to create a vertex buffer object. Don't worry about it. We have to bind both of those and load the VBO with our vertex data. We call a function called GL vertex attrib pointer, which tells OpenGL about the vertex attribute the data refers to, in this case, just the positions. We need to call GL enable vertex attrib array, which makes the last step actually do anything. I forgot this step once and spent hours pulling out my hair because of it. And in each render loop, we bind the shader program, we bind the vertex array object, we call GL draw triangles to draw the triangles, and voila. On the left is the filled quad, and on the right is the same quad in wireframe. The next step is a textured quad. To get the image data, we use another library called STBI image, which does a great job of loading images in any format we please. We bind it, we use GL text image 2D to send the data to the GPU. Back in our vertex data, we need another attribute, the UV coordinates. That tells OpenGL which parts of the texture we want to draw where. Like with the positions, we need to tell OpenGL about the new attribute. We need to tell the vertex shader to read this attribute and pass it along. We need to tell the fragment shader about the texture and sample from it, and where to sample from it to color in our pixels. And finally, we have a textured quad showing up on the screen. Of course, we're not done yet. The image is all stretched and distorted, and we only want one cell visible at a time. To solve these problems, we need... This is where the Dark Souls music plays. Okay, don't be scared. Try to shake off your Algebra 2 trauma. I didn't learn any of this crap in high school or college. I'm a history major. We're going to get through this. We're finally going to give the vertex shader something to do. First, we need a projection matrix. In our case, we want an orthographic projection. What does that mean? Well, in short, no matter how far something is from the camera, it should always appear the same size, in contrast to a perspective projection in a 3D game. A lot of 2D games are actually 3D with an orthographic projection. Then we need a matrix to scale the image. Right now, it's just in the upper right pixel. We need to stretch the sprite out to its full size. We need to perturb the UVs. I love that word, perturb. We need to perturb the UVs to only sample part of the texture, and then scale and translate those suckers. And then we need to animate the UVs and show one frame, and then the next, and so on at regular intervals. And we're back. Drink it in. I had to skim over a lot to get this talk under time. And graphics programming is hard, but it's also fun and rewarding, at least for me. You should probably use a game engine that does this for you. Learn OpenGL is how I learned any of this crap. LearnOpenGL.com is how I learned any of this crap, and I freebooted a bunch of slides from them. And I am also going to plug Jade's art again, because it's lovely. Are there any questions, comments, concerns, angry diatribes? Yes.
Why did you decide to go to learnopengl.com and start learning this?
I mean, it's just so rewarding. No, I mean, I like knowing how things work, and we're using a lot of libraries, and we're using a lot of abstraction, and to a certain point, you can only get so close to the graphics card. But yeah, I mean, the technical side of it, the how everything works side of it is really interesting to me. And I think there's value in knowing how all of this stuff works, even if you are using a higher level game engine. Especially when you do have to interact with some of those lower level elements like writing shaders in Godot or Unity or whatever. Any others? Yes.
So, like if I was using a game engine,
Uh-huh.
I'd be able to just like toss that in and say, all right, animate this, go.
Yeah, again, this would take you 2 minutes in Godot.
Right. What would you say the proportion is, like how many lines of code would this be to do that?
Well, you know, lines of code are a questionable measure of code complexity, but I mean, dozens? Dozens is probably right. Again, we're using a lot of libraries and things, so it's
Right,
like,
of course. I mean code that you would have to sit down and put out yourself.
yeah, like dozens. Dozens of lines of code. Not too bad. Anyone else? Yes.
When are we getting the Vulkan version?
That is a really good question. That is when I can be bothered to learn Vulkan, which hasn't happened yet, but we'll see. Yes.
Curious to know what your like aha moment was when working with OpenGL. Do you have a moment where you realized that things were fitting together, and what was that thing, or is it just constant pain?
It's not constant pain. It's intermittent pain, certainly, but it's not constant. And I don't know, when I'm working on any kind of difficult technical problem, I vacillate between feeling like the biggest moron that's ever existed and a genius. And the line that separates those two is just wafer thin. So to the extent that I'd say OpenGL clicked, I mean, I've done the thing. I've done it before. This part doesn't scare me. There are things that I haven't done yet. Like, for example, I want to get around to writing an SSAO filter. Which basically is a shader that makes the crinkly bits of objects look darker to emulate how light bounces around. So there's always more to learn. There's always more stuff. But in terms of like getting some code together and putting some 2D sprites on a screen, it's not actually that bad. Did that answer your question?
So when you code in Godot, which I know you also do code in Godot,
Right.
does all this knowledge, does it change how you go about writing graphics shaders in Godot? And what's that sort of looking like?
I have a confession, which is I actually avoid writing shaders in Godot whenever I can. Yeah, I know. I'm always, there's lots of impressive things that you can do with shaders, and the beautiful thing about using an engine like Unity or Godot or whatever, especially Godot, you know, they have like a shader graph tool. That's great. That's awesome. That means you don't need to write any code. You can do lots of really cool, expressive things without knowing what a graphics API is at all. So the modern high-level engines do a good job of insulating you from the gnarly low-level details, and that's good. However, sometimes those tools do fail you. sometimes those tools do require you to start to drill deeper and start writing GLSL shaders or whatever. And at that point, yeah, I think this background is helpful. But for 90% of Godot users, it's certainly not necessary. Anybody else? Wonderful. Well, thanks for listening to me ramble.